All right, folks, let's continue on with the section 3.1 content. We're going to jump into page 3 now. And page 3 starts with an example, salads at McDonald's. Again, McDonald's, haven't eaten there since my kids wanted a Happy Meal, which was at least a week or two ago. All right, McDonald's restaurants offer a variety of salads. The table below lists 10 different salads, along with the amount of sodium in milligrams and the amount of fat in grams, based on their published nutritional information. I'm not sure why we're talking about sodium and fat. Perhaps those things are bad and we don't want to consume them in large quantities. The data for this these two quantitative variables are shown in the scatter plot here to the right. So I don't want to miss this point that when we're looking at a scatter plot, it is paired data. So for this Southwest salad with grilled chicken, it has a sodium content of 650 milligrams and a fat content of 8 grams. So if I were to look for that on the chart, I would find it right there. So that point right there is this point in the scatter plot corresponds to the Southwest salad with grilled chicken. Okay, what we're asked to do here is describe the relationship between sodium and fat in McDonald's salads. Discuss any additional observations you have about the data. And I've given you a hint here, and that is to look at the clusters. So I'd really like you to shut down the video now and do some of that analysis on your own without just watching me pull the solution out. So take a look at the data and see if you notice anything. You should pause the video now. No, seriously, pause it now and do the work on your own before I show you mine. Thank you. Okay, hopefully you did as instructed, and I do want to show you a couple things here that I noticed when I was looking at this this graph. First of all, if I were to just consider the general shape of the graph, it's curved, right? It's clearly curved, but I want to dig a little deeper than that. I noticed I kind of highlighted that one point for this grilled chicken salad and said, or the grilled Southwest salad with grilled chicken. Let's take a look at some other ones. Let's look at the Southwest salad with crispy chicken. So that was in the 820 range with a fat content of 21 grams. It's probably this guy right here. Let's take a look at the Southwest salad without chicken. That's 150 on the sodium scale, 4.5 on the fat scale. Oh, look at this. Bacon ranch salad with grilled chicken. Why do we have this obsession with bacon? I don't understand that. I mean, it's okay, but it's not like I'm, elbowing people at the store to get to the bacon, the bacon section. Okay, bacon ranch salad with grilled chicken. I got 700 calories, and I got 9 grams of fat. Looks like it's that point right there. And next one is the bacon ranch salad with crispy chicken. That's a whopping 870 grams of sodium and 22 grams of fat. And then let's look thirdly here at this other bacon ranch salad without chicken. 300 on the sodium scale, 7 on the fat scale. So it looks like it's about right there. Last but not least, let's go look at the Caesar salad with grilled chicken. That's 580 sodium, 5 fat. Looks like it's this guy right here. And then we've got the Caesar salad with crispy chicken, the 740 and 18 grams of fat. And then the Caesar salad without chicken, 180 by 4. Then you get this little side salad down here. Why bother? Seriously, 10 calories. Okay, so take a look at that, folks. I hope you can see that there is a clear pattern there, that these clusters of points depend on what type of chicken is in the salad. I kind of used yellow there for grilled. I used green for crispy. And I used blue for no chicken. And that pattern kind of holds throughout all the different types of salads at McDonald's. So let's go ahead and take a look at what my analysis was here. Positive association between sodium and fat content. McDonald's salad, clearly as sodium goes up, fat goes up as well. Salads with higher sodium content also have higher fat content. That sentence right there, let's take a second to talk about that sentence right there. That sentence is describing the association in context, and as I said previously, that's required any time you are discussing the association between two quantitative variables. All right, the relationship is fairly strong, but it is not linear. The scatter plot shows a curved pattern, and we discussed that previously when I said, yeah, I see a general kind of curvature to this data. Interestingly, there are three clusters of points: upper right, lower right, and lower left. Those clusters correspond to salads with crispy, grilled, and no chicken. Even more interesting is within each of those, take a look at what happens within each of those. It's fairly linear within each of those different types of salads. And again, this guy up here was, this is my grilled patch or grilled cluster, crispy, and no chicken. All right, folks, next thing we're going to do is we're going to actually look at an applet from our textbook publisher about correlation and regression. So I'm going to kind of bounce back and forth between that and the notes, but what I am most interested in you actually working with the applet, not watching what I think you should be getting from the applet. So I have sent you the link to the applet in your school email. But in case you don't have that handy right now, that is the URL for the applet. And when you open the applet, it should look like this. Okay, the scatter plot displays the form, direction, and strength of the relationship between two quantitative variables. That's what we're working with now. I'm going to let you play with the applet a little bit, but I'll start by kind of doing the first thing for you here. It says you're going to use the correlation and regression applet to make several scatter plots with 10 points that have a correlation close to 0.7. So that's what you're tasked to do here. And the first part says start by putting 2 points on the graph. So I'm going to go ahead and add a point here and a point here. And right away it shows us our correlation is exactly 1. And I ask you this: what's the value of the correlation and why does it make sense? Why does it make sense that the correlation between 2 points would be exactly 1? Well, the answer to that question is correlation is 1 because 2 points determine exactly one line. So if I was to draw a trend line through those 2 points, there's only one line that would go through those 2 points. What I want you to do now is work through the rest of the directions for this activity. The directions are copied in your notes. They're also in the textbook on page 152. No need to get the textbook though because I've copied them for you. And there's a couple different places where I'm going to ask you to summarize some of your observations, and I will jump back into the video shortly and do that. So now is an appropriate time to pause and work through parts B, C, and D. In part B, you're asked to make a lower left to upper right pattern of 10 points with a correlation about R equals 0.7. So this might be what your applet looks like. I have 10 points here. My correlation, that's about as close to 0.7 as I'm going to be able to get. And I hope you notice that you can grab these points and then move them. And as you move them, the correlation changes accordingly. In part C, you're asked to make another scatter plot, one with 9 points in a vertical stack and at the left side of the plot and 1 point far to the right, and move it till you get a correlation close to 0.7. Now, here I have a vertical stack of 9 points and one off to the right with a correlation close to 0.7. In part D, we're asked to make a third scatter plot, this one with 10 points in a curved pattern that starts at the lower left, rises to the right, then falls again at the far right. Adjust the points up or down until you have a very smooth curve with correlation close to 0.7. Your scatter plot might look like this. Oh my gosh, look at that, I can't even count. I have 11 points, so let me get rid of one. Boom. Now I got to work on making this correlation closer to 0.7. That's close enough. Okay, so I got 10 points. I know that I said throughout the year that we're not going to be, this is not an algebra-based course, and we're not going to be using a lot of the things we learned in algebra, but I certainly hope that you recognize this is not a linear pattern. It is a curved pattern, but look at that. I got a correlation that's still about 0.7, which it was in the previous two scatter plots as well. From this point, we should be able to summarize that if we know the correlation between two variables is 0.7, what can you say about the form of the relationship? And the answer to that question is absolutely nothing. We've got to see a graph of the data to determine form, and that's a big idea with what we just did in this activity. If you just know that correlation is 0.7, that does not help you at all. Okay, it is fairly meaningless without a picture of the data, because we had three very different pictures, and one of them I would call the relationship approximately linear, but in the other two, clearly it was not. Okay, let's move on to page 4 now, where we are going to finish off this applet activity. Step 2 of this says, click on the scatter plot to create a group of 10 points in the lower left corner of the scatter plot with a strong straight line pattern with a correlation of about 0.9. And then add 1 point at the upper right that is in line with the first 10. How does this correlation change? Please do that now. So I'm going to go back to the applet now and take a look. I've got a scatter plot here with 10 points in the lower left-hand corner with a correlation of about 0.9. And then I was asked to add a point way in the upper right that kind of fits the overall linear pattern. I'm going to go ahead and put one right up there, and holy cow, correlation is about the same. Actually, it got a lot better. Okay, it improved our correlation up to 0.99. So go ahead and capture that observation in your notes. Okay, part B of this, step 2 of this activity, drag the last point straight down. How small can you make the correlation? Can you make the correlation negative? Please try that now. So if I take this point over to the right, the one that is clearly different than the overall pattern of the data, and if I take this point and drag it down, you'll notice that very quickly the correlation is decreasing. In fact, I can make the correlation negative by dragging this point to the bottom of the scatter plot. So we're asked to comment on that. How small can you make the correlation? Can you make the correlation negative? And I would say, yeah, you should be able to get a negative correlation if you pull that thing down far enough. So in step 2 of this applet, there are 2 different things that I hope you learned. I'd like you to think about those, perhaps talk to one of your table partners about it before you look at my observations. Okay, so from step 2 of this activity about the effect of a single point on the correlation, there are 2 takeaways that I think you should have. First, we should be recognizing that an additional point that matches the overall pattern of our data, even if it's far away from the majority of the data points, does not have a large effect on correlation. In fact, it can't even improve it. Second, an additional point that does not match the overall pattern of the data points can have a large effect on correlation. I don't want to say too much more about that right now, but when we get into section 3.2, we'll actually look in more detail at the 3 different types of relationships we could have with a point that doesn't match the overall pattern of our data. Okay, for now, it's time to wrap up section 3.1, and I have some overall comments on correlation, and here you go. The first one is, I want to talk about the formula. As I mentioned previously, this is a formula that you will not have to memorize, and you will rarely, if ever, need to use. In fact, this formula will be on the formula sheet for the AP Statistics exam. Okay, the formula for R is equal to 1 divided by the quantity n minus 1, where n is the number of paired values in our data set. Another way to think of that, it's the number of points in our scatter plot, times the sum, Greek letter sigma, of a product So a product here, we have two factors in that product. The first factor is x minus x bar divided by s sub x. And the second factor is y minus y bar divided by s sub y. So let's just pause for a second and think about this. Remember, with correlation, we're trying to describe a relationship between two variables. So one of those variables is x, the other variable is y. X bar is the mean of all the x coordinates in your scatter plot. S sub x is the standard deviation of all the x coordinates in the scatter plot. Same is true for y. Y bar is the mean of the y coordinates, and s sub y is the standard deviation of the y coordinates. Now I'm going to take one more step with this formula. It's the quantity 1, it's 1 divided by the quantity n minus 1 times the sum of something. I hope this isn't a stretch. If you look at x minus x bar divided by s sub x, you ought to recognize that as a z-score. That is really the z-score of the x variables. And then y minus y bar divided by s sub y is the z-score of the y variable. Okay, so that's what that is the formula for correlation. As I mentioned previously, not something you will use very often. We will get that from our calculator. Okay, some more comments on correlation. Correlation R makes no distinction between explanatory and response variables. In fact, if I switch the coordinates from explanatory response, if I actually reverse those variables and make the y coordinates the x coordinates and the x coordinates the y coordinates, I should have the exact same correlation. Another fun fact here for you on correlation: R is not affected by data transformation. So if I'm measuring something in pounds and then I change that to kilograms, my correlation should be the same. R is just a number. It has no units. Okay, it has no units. So we would never say something like, oh, the correlation is 0.85 meters per second. That's absurd. Both variables must be quantitative. And I mentioned this before, folks. This is an area where students could get tripped up on a test. If I ask you about the correlation between hair color and height, you ought to say that's absurd because hair color is a categorical variable, not quantitative. Correlation R is only a measure of the strength of linear relationships. Again, if we have a relationship that does not appear to be linear in a scatter plot, we should not be talking about correlation. Also, R is not resistant to certain types of outliers. And again, I mentioned that we will talk more about that in section 3.2 when we go into detail about linear regression. Just know that R is not resistant to certain types of outliers. R is not a complete summary of data. You still have to graph your data. Okay, and hopefully you recall that through that applet. If you don't graph your data, you could have the same correlation that's represented by completely different graphs. In fact, I'd like to show you a fairly popular picture of why R is not a complete summary of the data. So I'm going to go ahead and jump to another page here and show you this. Okay. So this, I wish I could give credit to whoever created this. This you can find pretty easily on the internet. If you Google something like dinosaur correlation, there he is. There's the dinosaur. So take a look. This is a scatter plot between X and Y. So we got X here and we got Y here. And notice that the mean of the X variables and the Y variables is not changing out to the nearest hundredth of a point. Same with the standard deviation. Out to the nearest hundredth of a point, it's the standard deviation for X is the same regardless of which scatter plot you're looking at. And notice the correlation. These all have the same correlation, negative 0.06. Again, that's a very weak correlation, but take a look at that. If I tell you that a correlation is negative 0.06, it would be inappropriate to say there's no pattern whatsoever in the data, because clearly there are patterns in this data. In fact, our friend the dinosaur there. So the message here is that correlation is not enough. You must also look at the picture of the data. I'm going to end with one final thought here. And one last idea about comments on correlation, and this is a big one, folks. Okay, you're going to hear this over and over again throughout the year. Correlation does not imply causation. So just because two variables are correlated does not mean we can say that one variable causes another. We're not going to say that the explanatory variable causes the response to happen without more evidence. And that will be a big part of what we do the rest of the year. All right, folks, that's it for section 3.1.